All right, we are getting ready to go live with Chegg's Pre-Calculus and Algebra Study Session Office Hour. As we wait for a couple people to roll in, though, before we begin, I just want to say thank you for joining us. Those of you that are logging in early here, we're going to get started in just 1 second as people are starting to log in. This is our Pre-Calculus and Algebra live session. So, without further ado, a big hello to everyone who's rolling in. Welcome to our live office hours for pre-calculus and algebra concepts brought to you by Chegg. I'm at Wallace STEM. You probably recognize me from my channel at Wallace STEM on TikTok, Twitch, Instagram, and other streaming services. Hopefully you're following me there. I like to take memes, trending sounds, and audios and make them about math. So I say come for the memes and stay for the math. It's lots of fun. For those of you that joined us here, though, for Chegg's office hour, welcome back. We're glad to have you here. But for those of you that are new here for the first time, the goal is to help you understand your your algebra and pre-calculus courses a little bit better. We're here every week to do just that. You can think about this like a virtual office hour, and I highly suggest you scan this QR code in the corner because that's how you can stay updated on the schedule of when these lives are. We are here every week to answer your questions, not just for algebra, but also for lots of other classes. So scan the code and make sure you're following along for that. Well, if you have questions, that's what this time is for. So please stick your questions in the chat and we will do our best to answer as many of your questions that come in about pre-calculus and algebra. Are you doing functions? Are you working with logarithms, exponentials? Are you shifting graphs? Are you completing the square? Are you factoring? Are you dealing with rational expressions? What are we working with? That's what we'll take a look at. Stick it in the comments. In my previous slide, there were lots of questions wanting to see an induction proof. So let's do a proof with induction to start us off today. So hopefully those of you that are asking about induction from the last slide, hopefully you've come back and joined us so that we can do a little bit of induction today. The idea of induction is we want to prove something is true by first looking at the base case, a case, and showing that it causes the next case to happen. I'll show you what I mean by that. For example, let's say I'm adding a bunch of numbers together. Let's say I'm adding 1 plus 3 plus 6 plus so on and so forth until I'm adding n times n plus 1 over 2. That's the formula that's going to generate the next number. That's going to ultimately be equal to n times n plus 1 times n plus 2, all divided by 6. We're going to show this is true using induction. The idea of induction is it's kind of like you've got a row of dominoes lined up. For those dominoes to fall, the first domino has to fall, right? So we're going to first show a domino is falling. Then the way another domino falls is it's going to be hit by a domino, which causes it to fall. So we're going to show that one domino hits another, causing it to fall. That way, we've shown the first one falls, and it's hitting a domino, and it's hitting a domino, and it's hitting a domino, and all those dominoes fall off. That is the idea of induction. So like I said, first we need to get that first domino and make the first domino fall. How we do that, we prove what's called the base case. And the base case, n is equal to 1, which means we've just got this first term of 1, and we want to ask, is it equal to this formula when n is equal to 1? Well, if I plug 1 in, we get 1 times 1 plus 1 times 1 plus 2. All over 6. Well, that's going to give us 1 times 2 times 3 when I do the adding, and 1 times 2 times 3, sure enough, is 6. And so 1 does, in fact, equal 1. We have shown that the first domino falls. That's the base case of induction. The second thing we're going to do is we're going to assume one of those dominoes is already fallen. It doesn't matter which domino. So we're going to assume it's true when n equals k. In other words, we're assuming one of the dominoes is falling. If n equals k is true, that means we've got this formula all the way up to k. 1 plus 3 plus 6 plus k times k plus 1 divided by 2. That's going to equal this formula with the k plugged in. K times k plus 1 times k plus 2 divided by 6. We're going to assume that's true, and we're going to prove that if a domino is falling, that's this one, it's going to hit another domino, making it fall. So we want to show, probably shouldn't underline to be consistent, we're going to show that n equals k plus 1 is true. In other words, we're going to go to the next term after k. So we're going to have 1 plus 3 plus 6 plus, we're going to include this k times k plus 1 over 2, but then we're going to go one term further. We're going to go to k plus 1. We're going to look at the next domino, which is when we plug k plus 1 in here. And this becomes k plus 1 plus 1. Adding 1 twice gives us k plus 2 over 2. We want to show that's going to be equal to this formula when we plug in k plus 1. So n becomes k plus 1. N plus 1 becomes k plus 1 plus 1, or k plus 2. N plus 2 becomes k plus 1 plus 2, which is k plus 3, all over the 6. Well, the way we're going to show this is true is we're going to acknowledge that all of this stuff was our assumption. We already know all of this stuff from our assumption is equal to this formula on the right side. So we can rewrite this as k times k plus 1 times k plus 2 all over 6. And we're just adding to it this new term, the k plus 1 times k plus 2 all over 2. Well, if I want to add these fractions together, we know in order to add fractions, we have to get a common denominator. In this case, our common denominator is 6, so we're going to multiply the top and bottom by 3. When I do that, then I can notice that I can write them all underneath a denominator of 6. But look at this. They both have a k plus 1 in common. I'm going to factor out that k plus 1 that they have in common. But look at this. They also both have a k plus 2 in common. I'm going to factor out the k plus 2. What's left is k plus 3. K plus 3. And notice what we end up with is exactly what we were trying to prove. That shows by the induction hypothesis, that 1 plus 3 plus 6 plus all the way down times n plus 1 over 2, this original left side is equal to the original right side. In other words, we showed one domino is falling. We showed if a domino is falling, well, actually, let me say that again. We showed the first domino is falling. We also showed that a domino is falling. And then we showed if a domino is falling, it's going to hit the next domino, which means it hits the next domino, the next domino, the next domino, the next domino, and goes all the way down, and proves this is true by the induction hypothesis. So that is an example, was asked about in the last slide, of how does induction work. That's what it does. We prove the base case when n equals 1. We assume it works if n equals k, and then we show it works if n equals k plus 1. This is also a great example of an application or a use of series. And another question came in about series. We're going to go over series and sequences. Now, that's a really broad topic. Usually, you can do a whole chapter on sequences and series. So I'm just going to talk really briefly about a geometric series. It's a special type of series where to get the next number, we multiply by a thing, whatever that thing might be. So for example, I might have 1/3. And then to get the next number in the sequence, I multiply by 1/3 again, and I'll get 1/9. And then to get the next number in the series, I'll multiply again, and I'll get 1/27. I get 1/81, and I keep multiplying by 1/3. And it just keeps growing. It actually can go on forever. What's really cool about geometric series is we can actually figure out what all of these numbers add up to. We can add up an infinite number of things and figure out what that solution is. The way we do that is we say the sum of all infinity numbers is the first number, which we represent with a sub 1, over 1 minus that ratio that we're multiplying by. In this case, the first number is 1/3. So our sum is 1/3 divided by 1 minus the ratio. And what we're multiplying by every time is actually the same thing. We're multiplying by 1/3 every time to get to the next number. So we'll do 1 minus 1/3. Now, a nice little trick that we'll use often with rational expressions is anytime you see a little fraction inside of a bigger fraction, the way we get rid of it is we're going to multiply top and bottom by that denominator. Now, it has to distribute all the way through, so I'll write it all the way through. And then when we reduce out the 3's, we get 1 over 3 minus 1, or 1/2. Which means if I add 1/3 plus 1/9 plus 1/27 plus 181 plus and keep going, I'm going to end up with 1/2 for my infinite sum. But let me show you something else that's kind of cool about geometric series. I know you're probably familiar with, just from your calculator, the idea of a repeating decimal. So if I had a repeating decimal of maybe 0.44444444, and it goes on forever, right? This first 4, you can think about that as 4/10. The second 4, you can think about that as 4/100. The third 4, you can think about that as 4/1000. And keep going. Well, this is a geometric series. So we can say the infinite sum of this series is equal to the first term, which is 4/10, divided by 1 minus what are we multiplying by to get to the next term? Well, the 4 doesn't change, so it's getting multiplied by 1. But to go from 10 to 100 to 1,000, we're multiplying by 1/10. So that common ratio we're multiplying by is 1/10. Doing the same thing we just did, if you multiply top and bottom by that denominator of 10, we end up with 4 over 10 minus 1, which gives us 4/9. And that's how we can take a repeating decimal and change it into a reduced fraction using geometric series and their properties. Excellent. Great question about series. What's really cool, and I won't spend time on it now, but what's really cool about geometric series is look at the decimal for 0.99999 repeating and see what fraction that equals. And it might surprise you and give you kind of an unexpected result, and you might think it's wrong, but it's actually right. So that's your homework for tonight. Look at 0.99 repeating and see what that decimal is equal to. And if you get lost, you can Google it. There's a lot of cool things out there. But anyways, this is your pre-calculus and algebra study session. There are so many topics in pre-calculus and algebra that we can talk about. So put in the chat what you want to talk about. Somebody brought up matrices. Let's talk a little bit about matrices. I don't know how to find the Jordan basis. The basis of a matrix is a little bit advanced, but we can play with matrices a little bit. Let's multiply matrices. And while we're multiplying matrices, if you have a question from your algebra or pre-calculus class you want us to look at, stick in the chat. We'll do our best to answer it here from Che today. So let's multiply two matrices. Let's multiply 2, 1, 3, 4, -1, -3. And we're going to multiply it by the matrix 2, 4, 1, and -1. Yeah. One thing to note is that this matrix, first matrix, has 3 rows and 2 columns. The second matrix has 2 rows and 2 columns. In order to multiply matrices, the center numbers have to match, and the outside numbers are going to be the dimensions of your matrix solution. So what we're going to do that is you're going to start off with the first row, and you're going to multiply it by the first column. So we'll do 2 times 2 is 4, and 1 times 1 is 1, and you add those together. Then we're going to do the second row and multiply it by the first column, and we're going to put it in the second row, first column. 3 times 2 is 6, plus 4 times 1 is 4. Then we'll do the third row and the first column. -1 times 2 is -2, and -3 times 1 is -3. So we'll do each row by the first column to get the first column of our solution. Next, we're going to do the same thing, but now we're going to do it with the second column. So we'll do the first row times the second column. 2 times 4 is 8. 1 times -1 is -1. Second row, second column. 3 times 4 is 12. 4 times -1 is -4. Third row, second column. -1 times 4 is -4. -3 times -1 is a +3. And now to get my final result from multiplying those matrices, I just have to do the arithmetic that is in there. So 4 plus 1 is 5. 6 plus 4 is 10. -2 and -3 is -5. 8 minus 1 is 7. 12 minus 4 is 8. -4 plus 3 is -1. And sure enough, we got a 3 by 2 final matrix, just like we expected. So, for those that are joining us, welcome. We are so excited to have you here. This is Cheg's live office hour to look at pre-calculus and algebra. Let us know what questions you have from your classes. Are you working with functions? Are you doing shifting functions? Are you working with composition of functions? Are you working with logarithms and exponents? In fact, let's do a logarithm and exponent problem because these are some of my favorite algebra problems. Logarithms are so cool in what they can do. The idea of logarithms and exponents is they help us solve problems like 5 to the 2x minus 1 equals 7 to the x plus 3. Logarithms have a real nice property that they can remove things from an exponent. So I can take any log base I want. Let's do a natural log because it seems smart because it's ln. It seems kind of prestigious. I don't know. You could use a regular log base 10. That works too. But the nice part about an ln or a natural log is it's going to grab that exponent and pull it out front. It's the most important property of logarithms. Grabs that exponent and pulls it out front. So when this exponent moves out front, we get 2x minus 1 is going to be multiplied by the natural log of 5. On the right side, the x plus 3 comes out front, and it's going to be multiplied by the natural log of 7. Now, natural log of 3 and natural log of 7 will probably feel a little weird and strange, but they're just numbers, and it actually would be more difficult to deal with the ugly decimals. Let's keep them as natural log of 5 and natural log of 7. Just remember, it's just a number. And we're going to solve by distributing that through the parentheses, giving us 2x times the natural log of 5 minus the natural log of 5. And then I can distribute through the parentheses to get x natural log of 7 plus 3 natural log of 7. Remember, our goal is to solve for this x. Being on two sides of the equation makes it really difficult to solve for. So to make it easier to solve for, we're going to put all the x's on one side. Let's subtract x natural log of 7 from both sides. Putting all the x's on the left side. Natural log of 5, though, doesn't have an x. So let's put everything without an x on the right side. We're going to add the natural log of 5 to both sides. Now I've got 2x natural log of 5 minus x natural log of 7. That's equal to 3 natural log of 7 plus the natural log of 5. Again, it looks really weird with all those ln natural logs in there, but that's okay. We can still handle that because they're just numbers. We're really after figuring out what this x is. So we need to get these x's together. What's nice is when they're on the same side of the equation, they can factor out. When I factor it out, I get x times 2 natural logs of 5 minus 1 natural log of 7. Still equal to 3 natural log of 7 plus the natural log of 5. And then I can get the x alone by dividing both sides by this thing that x is multiplied by, no matter how ugly it is. 2 natural log of 5 minus the natural log of 7. 2 natural log of 5 minus the natural log of 7. Because when I divide it out, it reduces, and I get x is equal to 3 natural logs of 7 plus the natural log of 5 over 2 natural logs of 5 minus the natural log of 7. If you're going to put this in your calculator, you need to be very careful, though, because probably the most common thing I'll see is everyone will do this much perfectly. Then they put it in their calculator, and weird things start to happen. When you put this in your calculator, because there's multiple things happening in the numerator and denominator, you need an extra set of parentheses around that entire numerator and that entire denominator. Also, most calculators, when you hit the natural log button, will open a parentheses for the natural log. So you need to tell it that we need to close the parentheses on each of these as well. So you need to make sure you get all of those parentheses on there. And then let's see if I can plug this into my calculator really quickly. Parentheses 3 natural log of 7, close the parentheses, plus the natural log of 5, close the parentheses on the natural log, close the parentheses on the whole thing. There's 2 there. Divided by, open a parentheses, 2 natural logs of 5 minus the natural log of 7. Close the parentheses on the natural log, close the parentheses on the whole thing. And I think I'm getting 5.85. That means if I were to plug 5.85 into this exponent, we'll get the same thing on both sides. If I do 5 to the 2 times 5.85 minus 1, and if I do 7 to the 5.85 plus 3, sticking 5.85 in for these x's, I should get the same thing. They should be equal to each other. Let's find out. 5 to the 2 times 5.85 minus 1. That's going to be, oh, this is a huge number. 301280606. Maybe 07 when I round. So I'm rounding. We'll see if I get a round off error here. Then I'm going to do 7 to the 5.85 plus 3. And sure enough, I get 301.38223. So it's off by a little bit, but that's because I rounded this number. The actual number there was 5.850250719 if I had done all the decimal digits. But you see, it's got the same number of digits. Starts out pretty much the same. We're off by less than 1% of 1%, which is really good there. So that's the idea of logarithms and how they can help us solve by taking the natural log of both sides. They have this beautiful property that grabs the exponent and pulls it out front. So hopefully that helped get you going there. Question just came in about parametric equations. So let's take a move over to GFOSO's question off of YouTube about parametric equations. Parametric equations, there's a lot we can do with parametric equations. And when you get to calculus, you'll do a lot more with them. But at this point, we're just going to introduce them. The idea is that we want x and y to both be independent variables based on time. Often you'll see this happen. You'll see this happen when we're describing how something is moving, and it's moving in multiple directions. So we want to know. Excuse me. No, I almost sneezed there. Didn't want to sneeze into the microphone. you'll see, like, we want to know how far it's moving in the x direction, how far it's moving in the y direction. So maybe we'll have some function like x is equal to t squared minus 5. And maybe y is equal to the square root of t plus 6. And so it's kind of moving in the x direction, the y direction at this pace, at this speed. It kind of helps you draw out the graph in parametric form. We could have a z equation too, so we could go in 3 dimensions, but the idea is exactly the same. One thing we want to do, though, is kind of get an idea of what shape this is going to be as it gets graphed out. It's kind of hard to see in parametric form. We could test it by looking at values for t, and so we could say, well, if t is 0, x becomes 0 squared minus 5, which is negative 5, and y becomes 0 plus 6, so it's the square root of 6. And then maybe if t is 1, we get 1 squared is 4, 4 minus 5 is negative 1, but 1 plus 6 is the square root of 7. That's not a 7. And then we can start graphing these points and get an idea of what the graph is going to look like. But maybe a better way is to eliminate the parameter or eliminate the parametric equation. And the way we're going to do that is we're going to solve one of these equations for t. So for example, if I wanted to solve y for t, I could square both sides and I get y squared is equal to t plus 6, or t is equal to y squared minus 6. That's going to be nice because now I can go to the other equation and stick this t in for the t in the other equation, and that'll give me an equation that maps out the trajectory and the path of this object without the time variable. So we can get the actual equation that x is equal to y squared minus 6, all of that squared, minus 5. This one might be easier. Drop my pen, sorry. This one might be easier to solve for y if we first add 5 to both sides. Equals y squared minus 6 squared. And then we can get rid of the squared by taking the square root of both sides. So we get the square root of x plus 5 is equal to y squared minus 6. We should really have a plus or minus there because it's not a function anymore. That's the neat thing about parametric equations is when we unparametrize them, it often ends up in a non-function form. This one's going to get really interesting because now I'm going to add 6 to both sides. And so I get 6 plus or minus the square root of x plus 5 is equal to y squared. And then we're going to get kind of the fourth part of this function by taking the square root of both sides again. So we get plus or minus the square root of 6 plus or minus the square root of x plus 5 is equal to y. What an interesting relationship. It's not really a function. But this is what the thing is doing as it traces out that graph. So that's kind of parametric in a real introductory form. Another thing that we do besides parametric equations might be polar equations to graph in a slightly different way. That uses a lot of trigonometry, though, so I'll save that for the trig live feed broadcast. Another request came in, though, for matrix multiplication while we were talking. So let's back up to that comment and let's do some more matrix multiplication so that we can practice with that. This is your live office hour with Che and at Wallace STEM to answer all of your questions about pre-calculus and algebra. Are you having problems with factoring? Let me know in the chat that you want a factoring review, maybe a rational expressions review. Maybe you want help completing the square. That's a really important skill that you learn in pre-calc and algebra. Maybe you need help solving equations, solving quadratics, solving radical equations. Stick in the chat, tell us what you want to take a look at, and we will do our best to answer those questions. But I said we were going to do some more matrix multiplication. Let's practice with just a simple 2 by 2 matrix of 1, -2, 3, and -4. And we're going to multiply it. That's a 2 by 2 matrix. We're going to multiply it by a 2 by 1 matrix. Remember, these middle numbers have to match. So that means 2 rows, 1 column. let's call it 5 and -1. When we multiply matrices together, the result is going to be the dimensions of the outside. This is going to be a 2-by-1 resulting matrix. So we're going to multiply each row by each column. So when we multiply, we'll take the first times the first plus the second times the second. So we have 1 times 5 is 5, and -2 times -1 is a +3. Then we'll take the second row and multiply it by this first column. 3 times 5 is 15, and -4 times -1 is a +4. And so that is our matrix multiplied together, 8 and 19, that we're going to get when we multiply those together. So that's matrix multiplication. Thanks for asking about it. One of the fun things we can do with matrices, though, is instead of just multiplying them together, we can actually find their inverse. What's interesting about their inverse is you're looking for the matrix that when we multiply 8 matrix, we'll call it matrix A, times matrix A's inverse, you're going to end up with the identity matrix. The identity matrix is the one with 1s up and down the diagonal, and everything else is a 0. And the way we do that is with what we call matrix operations. So for example, if I've got a matrix that's 5, -2, 1, and 3, we're going to make it into an augmented matrix, which means we kind of squish 2 matrices together with the identity that's got 1s down the diagonal and 0s everywhere else. And then we're going to start doing what are called row operations to this matrix. In other words, we want to make this side be 1, 0, 0, 1 and make this side into the inverse matrix. And it's really cool what happens when we do that. So to do that, we need to make this 5 into a 1. The way we do that is we take that entire row 1 and we're going to find out what 1/5 of it is. And that's going to become the new row 1. So when we take 1/5 of row 1, 5 becomes 1. -2 becomes -2/5. 1 becomes 1/5, and 0 times 1/5 becomes 0. Didn't do anything to change row 2, so we'll keep that exactly the same. Now what we're going to do is we're going to put a 0 underneath our 1. The way we make that into a 0 is we're going to take row 1, which is already a 1, and we're going to multiply it by the opposite of what's in row 2. We're going to multiply it by -1, and we're going to add it to row 2, and that's going to give us our new row 2. So what that basically means is the first row doesn't change, 1, -2/5, 1/5, and 0. The second row, we're going to multiply this by -1, giving us -1 plus 1, which is 0. We multiply this by -1, giving me 2/5 plus 3. Common denominator, I'll call that 15/5. 2/5 plus 15/5 is 17/5. 1/5, -1/5 plus 0 is -1/5. And 0 times -1 is 0 plus 1 is 1. All right, we've got 1, 0. Like we wanted. We're halfway there. We need to make this into 0, 1, and then we'll have our inverse. The way we're going to do that is we're going to get a 1 down here. We can do that by multiplying by this reciprocal. We'll multiply by 5/17 times row 2 to get our new row 2. And so when I do that, row 1 doesn't change. It's 1, -2/5, 1/5, 0. Row 2, we're going to multiply everything by 5/17. So 0 times 5/17 is 0. 17/5 times 5/17 is 1. -1/5 times 5/17 is nice because the 5s reduce out, giving me -1/17. And 1 times 5/17 gives me 5/17. We're almost there. We've got 1, 0, and a 1. We need to make this one up here into a 0. And the way we're going to do that is we're going to take row 2, which has a 1 in it, and we're going to multiply it by 2/5, making it a negative 2/5 to add to the row 1 to give us our new row 1. So when we do that, 0 times 2/5 is 0, plus 1 is 1. 1 times 2/5 is 2/5, plus negative 2/5 is 0. Well, I'm not going to be able to do this mental math anymore, so we're going to have to write it out. So we've got 2/5 times negative 1/17, and we're going to add that to 1/5. So that's going to give me negative 2 over 50 plus 35 is 85. And we're going to add that to getting a common denominator, 17 over 85. Which is going to equal 15 over 85. This is why I don't make up problems on the spot, because it's going to give us negative, ugly numbers. But we were able to manage. We've got 15 over 85. I see someone put in the comment from TikTok, Frenick, reduced row echelon form. That's exactly what we're doing to this matrix over here, is we're getting that reduced row echelon form. So exactly right. Now I'm going to take this number times 2/5. So let's get this work out of the way. We're going to take 5/17, and I'm going to multiply it by 2/5, which is nice because the 5s reduce out, giving me 2/17. And I'm going to add it to 0, giving me 2/17. The second row stays the same. It's 0, 1, negative 1/17, and 5/17. And notice we've taken the identity matrix from the right side to now get the identity matrix on the left side. When we've done that, the thing over here is the inverse of our 5, negative 2, 1, 3. That's going to be 15/85, 2/17, negative 1/17, and 5/17. When this matrix gets multiplied by that matrix, it results in the identity matrix, or it gives us 1. It's kind of a complicated process, or it feels that way at first, but really it's just something we need to have practice with and do lots of to get really good at. And that's true about almost anything that we do in math. One example of that would be piecewise functions. So let's transition away from matrices, and I want to talk about piecewise functions, because this is your review of pre-calc and algebra questions that you may have. So tell me what questions you have about algebra and pre-calc. Tell me what topics you're working on right now in your algebra and pre-calc classes, and we will take a look at doing those exact things. And the question came up to do some piecewise functions from TikTok. So the idea of a piecewise function is it's not just f of x equals some number, but it equals some options of numbers. For example, it might be x squared minus 4 if x is greater than 0. And then it might also be 2x minus 1 if x is between negative 1 and 1. And it might be the square root of negative x. Well, that's probably getting too complicated. Let's keep it simpler. Let's just do 3 if x is less than negative 1. And we need some or equals 2, so we'll put some or equals 2 on that. And maybe we want to try and graph this piecewise function. So what we're going to do is we're going to kind of think about what's this function doing at all points. And then we'll kind of focus our attention to just the domain restriction. So our first function, I'm going to do this in blue, is x squared minus 4. We recognize x squared. That's the parabola, right? We know the parabola shape of x squared. The minus 4 is going to shift it down 4. So it's going to be a parabola shape down 4. So, 1, done. So it's going to be this shape. This is the parabola shape. right? But we're only going to do this parabola shape when x is greater than 0. So x starts out here at 0, and then as this graph comes up, that's going to be greater than 0. And you notice I did a solid dot here. We do a solid dot because we have that or equals to. We would do an open dot if it was not or equals to, and we don't really care what happens to the graph before 0. Then we're going to take a look at the second part of the graph, and that's what we're going to graph if x is between -1 and, oops, I can't have overlapping. Let's go from, let's back everything up by 1. Sorry, let's go from -2 to 0, and when x is less than or equal to -2. Give us a little bit of space to work with. So 2x minus 1, we know that's got a y-intercept at -1, and it's a line with a slope of 2. But I'm only going to go between -2 and 0. So -2 is here, and 0 is here. So if I go backwards, I'm going to do a slope of 2, 1. Normally we would rise 2 and run 1. I'm going to rise -2 and run -1. Rise -2 and run -1. And that last one needs to be an open dot because at -2, we're not actually equal to. And so it's going to give me that slice of the entire line that we normally see. Finally, the last part of this piecewise function is when the function is equal to 3. And so that happens when x is less than -2. So here's 3, right? That's where y is equal to 3 or f of x is equal to 3. But we only want that from -2, from this point, down, less than. All the rest of this graph can go away. And that's the idea of a piecewise function, is there's going to be these jumps in the graph. The technical term is they're jump discontinuities, because this is the x squared minus 4. Then we jump to the 2x minus 1. Then we jump to 3, and that's going to be our function. These are really useful when situations change. So, for example, if you're driving down the freeway and there's an accident up ahead, you have to slam on the brakes. Your velocity or your motion or your momentum or your acceleration is going to change in some way. So the graph is going to change directions and change shapes. And that's kind of what's happening with the piecewise function. If nothing changes and everything stays the same, it'll follow a nice little trajectory. But something might change, throw off the trajectory. You could think about this as there's something kind of moving through space, maybe in the asteroid belt, and it's revolving around the sun in a nice elliptical shape. And it's a very predictable elliptical shape until some point in time it collides with another asteroid, and that shoots it off out of the solar system, maybe in a hyperbolic direction away from the sun, breaking the force of gravity from the sun. So lots of applications of piecewise functions when something changes our situation and now the graph looks different. Great question came in though, just as I was explaining my little example about space, is what about, I can erase all these spots. You see all those spots? These spots are really dark for me. They're kind of annoying me. What about rewriting expressions using the properties of exponents? Great question. Properties of exponents are so important because they can simplify problems that are very complex into problems that are much simpler to work with. And I think you even mentioned that you wanted rational exponents with properties of exponents. So let's say I've got an expression like 5 times x to the 2/3 times y to the 1/2. The entire thing is squared. Then I'm going to multiply by x to the 1/6 times y to the 1/4. And that's all going to be over, let's do x to the 1/2, y to the 2nd. We'll do a whole power there. All right, so how do we simplify this expression? Lots of things going on here. I kind of like to think about when I'm simplifying, what do order of operations actually do? Order of operations tell me to simplify inside the parentheses first. So I look inside this parentheses, is there anything I can simplify? Not really. I can't combine x's, y's, and numbers together. So there's nothing I can do with the parentheses. The next thing we want to think about is our exponents. There is an exponent on this parentheses. And because this is all multiplication or division, we can put this exponent in onto each part of that expression. As we do, double exponents are going to multiply. In other words, a to the b raised to the c power. Those double exponents are going to multiply to give us whatever b times c is. Now be careful, because the common error I'll see people do here is they'll say, well, so we do 5 times 2 to get 10. No, we are multiplying exponents together. 5 has an exponent of 1. We'll multiply the exponent 1 times 2 and get 5 squared. 5 squared is 25. Then on the x's, we'll do 2/3 times 2. Remember when we're multiplying fractions, it might help to write this as 2 over 1. Multiplying fractions, we multiply straight across. So 2 times 2 is 4. Over 1 times 3 is 3. So we have x to the 4/3. On the y, we've got 1/2 times 2. Multiplying across, we've got 2 over 2. 2 over 2 is actually pretty nice because 2 over 2 reduces to 1. So we've got y to the 1st. Everything else is still the same. We got x to the 1/6, y to the 1/4, all over x to the 1/2 y squared. Now that we've gotten rid of the parentheses and the double exponent, now let's see about combining these x's together. When we're combining these x's together or combining these y's together, we've got another property that says if some base is raised to an exponent and that base is raised to another exponent, we know we can add those exponents together. So we're going to add 4/3 plus 1/6. How do we add fractions? We need a common denominator. So the common denominator here is 6. I'm going to multiply by 2 to get 8/6 plus 1/6 is going to equal 9/6, which we can reduce to 3/2. So when I combine the x's together, we get x to the 3/2 power. What about the y's? 1 plus 1/4. Well, 1 is 4/4 plus 1/4 is 5/4. So we have y to the 5/4. Over, we still have x to the 1/2 and y squared. Almost done simplifying. We know we're done simplifying when there's only a single x and a single y. We've got 2 x's and 2 y's. So to simplify these, over division, we've got another property that says when we have the same base over division, we're going to subtract those exponents, giving us b minus c. So, and for the x's, we have 3/2. We'll take away 1/2. 3 minus 1 is 2/2. 2/2 reduces to 1. We don't usually write 1 as an exponent, though. We'll leave that as an x. For the y's, we've got 5/4 minus 2. Well, if I do 5/4 minus 2, I need to get a common denominator again in order to subtract those. So my common denominator is going to be 4, giving us 5/4 minus 8/4. That's going to give us negative 3/4. So we end up with y to the negative 3/4. The problem is we don't usually like negative exponents. Fortunately, we've got another property of exponents that says a raised to some negative exponent is the same as 1 over a to that exponent. So let's move this down into the denominator just like that moved down into the denominator. When I do, I get 25x over y to the 3/4. And now we have simplified our expression with rational exponents using our properties of exponents. Want to take a screenshot? It's a beautiful problem. Excellent. Well, thank you for that question. It was a great question. We are doing a pre-calculus review, an algebra review, answering your questions. So what questions do you have? What topics from your algebra class would you like to take a look at so we can answer your questions and help you be successful in your classes? That's what Chegg wants to do today for you. I lost my pen again. I'm dropping those all over the place today. All right, so stick those questions. Let's keep the questions about pre-calculus and algebra. We'll talk about things like Green's theorem in the calculus study session. We're doing a calculus study session tomorrow afternoon, actually. If you scan this QR code, you can stay up to date on all of the schedule for Chegg's office hours that we are doing throughout the week. They are live every evening doing something different, doing economics, doing chemistry, doing physics, doing math, doing even advanced topics like linear algebra, statistics. Check out Chegg's schedule right now, scan this QR code, and we'll make sure we're answering all of your questions. I want to do a little bit of completing the square next, because that is probably one of the most essential topics, and it's probably one of the most misunderstood and underappreciated topics. It's actually very simple to do if you know the steps. So let's take a look at doing 3x squared minus 10x plus 5. And we're going to complete the square on this. And I intentionally did not make this equal anything, because if it equals something, there are some complete the square things that we can do. Hello, Albert. Thank you for logging in to Chegg's pre-calc office hour. Glad to have you joining us. This is not equal to anything, because when it's equal to something, the completing the square becomes easier. And then sometimes that becomes problematic because we don't learn the full process of completing the square. The full process of completing the square is, first we got to get rid of anything that's in front of your x squared. We're going to factor that 3 out. Even if it doesn't factor out nicely, it's going to factor out in forced fractions, and that's okay. Fractions are friends, not food. When we factor a 3 out of the 10, we get 10/3. It's just a fraction, that's okay. Plus 5. Actually, I'm only going to factor the 3 out of the first 2 terms, because completing the square really focuses exclusively on the first 3 terms. Once I've factored out that a, then what I'm going to do is I'm going to say, okay, we're going to find that magic number that is going to complete the square, or make this into something that factors into a plus b squared. To get that, we're going to take this middle term, the negative 10/3, and we're going to find half of it and square the answer. Well, when we do 10 over 2, that's going to reduce to 5. So we end up with negative 5/3, and we want to square that answer. Well, negative 5 squared is 25, and 3 squared is 9. That's the number that we need to add to complete this square of 25/9. However, we don't want to change the value of our overall expression. So to not change the value of the overall expression, if I add something, I also have to subtract the 25/9. And here's where we have to be careful, because I didn't actually just add 25/9. The 25/9 is inside of the parentheses multiplied by 3. And so I'm going to multiply that by 3, just like this was multiplied by 3. So I'm subtracting the same thing that's added in. Because when I do that, we'll end up with a perfect square right here. We take the square root of the x squared, that's x. We take the sign from the middle, minus. And then we take the square root of the fraction, which is 5/3. And then we've just got this other piece here that we need to look at. That other piece is all of this arithmetic. What's nice is 3 over 9 can reduce to 3. 5 gets a common denominator of 15/3, multiplying top and bottom by 3. 15 minus 25 is negative 10/3. And that becomes my final expression with my completed the square. Why do we care? What does that tell us? Why is that useful? It's useful because these numbers tell us where the vertex is of this parabola. The vertex is at 5/3, comma, negative 10/3. So if I wanted to graph this parabola, it does not factor, and so factoring is not going to help me. But if I go 1, 2, 1, 2, 1, 2, 1, 2, I'm going to break these down into thirds. So I'm going to put little tick marks every third along the way so that we can see how this graph's going to look. The vertex is at x of 5/3. That's 3, 4, 5/3. Y is negative 10/3, 9, 10/3. The vertex of this parabola is right here. And so we know now where this parabola is located because we were able to complete the square on this expression. The y-intercept's 5, so if this came up far enough, it's going to hit that 5, but I didn't make my graph big enough to show that. So completing the square is a really important skill for you to learn and master. It comes up a lot as you continue studying pre-calculus. It comes up again in calculus. It comes up again in a lot of different topics. So completing the square is one that's definitely worth solving. Well, we are coming close to the end of our time together. We've probably got time to do one more problem together. One thing that I always like to squeeze into our algebra discussions is a quick review of factoring, because factoring is one of the most essential foundational skills that you need to learn in algebra. It comes up in every topic, it seems, after you learn it. You learn factoring, then you learn rational expressions, where you factor. Then you learn trig and solving trig equations, where you factor. Then you do derivatives and antiderivatives, and the way you do the antiderivatives with partial fractions by first factoring. Then you do differential equations and you solve the auxiliary equation by first factoring. Factoring never goes away. So let's look at how I like to factor things such as 6x squared plus 7x minus 3. I like to use for factoring a method called slide and divide. There's lots of factoring methods, but the way slide and divide works is we're going to slide this 6 over and multiply it by 3. When we do, we get negative 18. So it's slid over, it's hiding inside here. It's 6 times 3 is negative 18. The reason we do that is this blue equation is actually easier to factor and solve than the black equation. So we're going to factor this blue equation first. And the way we factor this blue equation is we want two things that multiply to 18 and add to 7. Well, 18 is 9 times 2. And if the 2 is negative and the 9 is positive, it's going to add up to that 7x. Well, the brown here is only factoring the blue equation, not the original equation that we're looking for. So what we're going to do instead is we said it was slide and divide. We slid the 6. Now we're going to divide the 6 out. As I do, when I reduce these, any leftover denominators are going to end up being in front of the x. So 9 over 6 reduces to 3 halves. That extra denominator is going to go in front, and we have 2x plus 3. 2 over 6 reduces to 1/3. That extra denominator slides in front, and it's 3x minus 1. And this is the solution factored to the original top black equation. So that is my strategy for factoring. It's called slide and divide. Slide the 6 over to get something easier to factor, and then at the end, divide it out of both the numbers. Anything left in the denominator goes out front. Works every time. We are just about out of time today, though, so before we wrap up, I want to make sure you see in the chat, Chegg has been sticking in the chat. They are doing a promo code right now to save 50% off your next month of Chegg subscription. So do that with the promo code CheggLive50. Click the link in the chat. Make sure you're not missing out that opportunity. Also, scan this QR code so that you're aware of all of our future lives. We are doing a lot of lives to help you with all of your difficult subjects, because Chegg is here to help you 24/7 with your toughest subjects. So make sure you're checking them out. Thank you for sharing my love of algebra and pre-calculus with me today. I want to also make sure you are following Chegg here on TikTok, on Instagram, on YouTube, on Twitch. Also, make sure you're following me. I'm at Wallace STEM. You can see my, well, I was right there. At Wallace STEM is my handle, and you can follow me there on also all the same channels, all the same media. We are excited that you have joined us, but we are here every week continuing to help you be successful. So